Hello everyone, welcome back to Reverse Engineering Windows 32-bit applications. In this video, we are going to start addressing the topic of heap buffer overflows. So we spent quite a bit of time so far addressing stack buffer overflows. Now, stack buffer overflows that we said before are something that we've known about for quite a while and something that has been investigated quite a bit. So now we're going to look at something that's a little bit more recent and also a little bit more difficult to exploit in some cases. So heap overflows. In order to understand heap overflows, we need to understand heap variables. So what is a heap variable? A heap variable is something that you can use for variables that are dynamic. What does that mean? If I need some storage, but at compile time, I don't know how much I need, that's where a dynamic variable can come into play. If I know that I have 50 items, then static variables can work. Stack variables are just fine for that situation. If I don't know when I write my program and compile it how many things I will need, I can use instead a dynamic or heap variable to store my items. It is also suitable for larger items, objects, or structures, also large arrays. There's a limited amount of stack space. Now, in the olden times, there was a pretty good hard limit, and you could often use your compiler and say, this is the maximum size of a stack. Some of the newer compilers and newer systems have some flexibility with this, but in general, the heap is used for storing large items. Also, if I need something that will outlive its defining brackets, we say that variables live and die in the curly brackets in which they're defined. So if I create a variable in C or C++ inside of curly brackets, which could enclose a function or really just a chunk of code, that variable goes away when it hits the closing curly bracket. Other differences. Well, this is a manual process. So we have manual allocation and deallocation. Sometimes stack variables are called automatic variables because they are automatically created and destroyed. So in order to use the heap, we will have to use new in the case of C++, and then delete to get rid of the object. In the case of C, we can use malloc, calloc, and a whole family of functions to allocate memory, and then we have free, which is used to release that memory. Now, you should know that heap variables are slower than stack variables because there's a little bit more overhead. When it comes to the heap, there are different implementations out there. Many of these are named after people. So you will see their initials, DL malloc. The guy that invented that, his initials were DL. ptmalloc is another common implementation, common algorithm that's used. And this is especially important because this is what is used in recent versions of Linux using the GCC compiler. Some others that you might heard about out there: tcmalloc, jemalloc, nedmalloc, horde, and you can always do a custom implementation if you decide you don't like any of the other implementations out there. So there are quite a few different implementations of a heap. And why is this? Well, if you think about it, the heap has to manage all of this available memory. So how do I keep track of what's available and what's not available? What chunks of memory have been used? Which ones have been consumed? If I free some memory, how do I reuse it? How do I store what memory has been allocated and what's still available? All of these things can be done various ways. So there are various implementations that you might find in order to have a heap. And like many things, there's always the guy that decides that he doesn't like any of the other implementations out there, and they just decide to roll their own. Which is maybe not so bad for a heap implementation as it is for, say, encryption. Roll your own crypto is something that we all know is very, very bad in the InfoSec community. Okay, heap versus the stack. Heap is manual. We talked about that. You have to manually allocate and deallocate storage. Another difference: the heap is persistent. I can create a variable that outlives its brackets. So if I have something that I want to pass around, say from function to function, then I want to use the heap. The heap is also unlimited. I don't have a 4K heap, for example. So the heap is essentially unlimited. You might say, but you only have so much memory. Well, we have virtual memory. So essentially it's unlimited. Now, of course, if you exceed the actual physical RAM that you have, it's going to be plenty slow, and you're not going to be a happy camper. But it is not limited in the way that the stack is limited. It's a little bit slower. Why is that? There's a little bit more overhead. Allocating things on the stack is easy. You just subtract from the stack pointer. Allocating things on the heap, there's some more you have to go through. Also, there's a possibility that things are not stored in contiguous memory regions on the stack. In most cases, that's not true, however. In most cases, they are. Another important difference for us: we said that the stack grows down toward lower memory addresses. The heap, however, grows upward. So that's another important difference between these two constructs, heap versus stack. What about vulnerabilities? There are some programmers out there that will swear up and down, oh, well, problem solved when it comes to stack vulnerabilities. Just use the heap for everything. Then you don't have to worry about your sloppy programming. That is completely false. you still need to worry. You can't just say, well, it's all on the heap, so I don't have the stack overflow vulnerabilities that I once had. Generally speaking, if you're going to have a heap vulnerability that's exploitable, you will need more than one allocation. It's not strictly true. You could perhaps exploit a flaw in some code where there was only one allocation on the heap. You could overflow it so much that you can cause a program to crash or crash in a structured way, where you have a overwritten structured exception handler in the Windows world or some other kind of exception handler in the Linux world that's going to take over. So yes, you might be able to do something if there's only one allocation. However, normally you're going to want at least two. Also, let's look at this realistically. How many real-world programs only allocate one thing on the heap? Not too many. Not ones that you would be trying to exploit, at least. Like many vulnerabilities, it will normally require some unfiltered input from the user. So there is a part of the program that is flawed in its logic, in its use of heaps, and you're accepting input from the user in some manner over the network, command line, etc. And that is going unfiltered into your program, which allows one of the buffers to be overflowed into another buffer. Now, this is somewhat harder than stack buffer overflows. However, having said that, it is true that because we've known about stack buffer overflows for so long, there are many things in place to try to prevent you from exploiting these flaws. So when it comes to heap vulnerabilities, how do I exploit them? Two basic ways. I can overwrite the internal structures in the heap. These internal structures are used to keep track of which chunks of the heap are in use and which are free. So what can I do? I can overwrite these structures and I can cause my program to crash, do a denial of service or DOS attack. That is actually fairly simple to do. What's a little bit more challenging to do is to do some sort of redirection using the techniques we've already described here. So, we might override some sort of error handling code in order to change that DOS attack into something else, some other kind of an attack. The other way that we can exploit a vulnerability with a heap buffer overflow is we can overwrite data in adjacent buffers. What can we do with that? We could possibly redirect if the program logic depends on that data. So perhaps there's a variable, and based on the value in that variable, I'm going to branch to different parts of my program. By changing that data, I can go to different areas of the program that I normally wouldn't have gone to. This can also give me things such as privilege escalation. Perhaps I'm going to run something as a certain user. Well, if I can change that user to a privileged user, then I might be able to do something bad. I could also just change the data in order to maybe save myself some money, for example. Maybe I want to change the data so that I can change the price on some goods that I'm buying. So there are a lot of things that you can do with heap buffer overflow vulnerabilities that might not be immediately apparent when you first look at that. All right, well, this video is pretty much just an overview of heap buffer overflows and the kinds of things that can happen with them. In some future videos, we will get into some of the details and we will talk in depth about how we can find these vulnerabilities and how we can exploit them and a couple of different scenarios that we might be concerned with out there. But this is pretty much what I wanted to cover in this video. As a reminder, this video is just one in this course in a whole family of courses that we have here at Pen Tester Academy, your source for everything InfoSec. And I look forward to seeing you in this course or another course here soon. See you then.